This will be part 1 of chapter 14. So chapter 14, electrode potentials. This section is going to go through definitions and talking through galvanic cells. Now for the most part, everything in here should be review. Obviously a lot of definitions. Some of the definitions maybe go a little further on the physics side than you might have talked about in general chemistry. Again, for the most part, review, vocab. So, electrode potentials, we're talking about redox reactions. So a redox reaction is any chemical reaction where electrons are transferred from one substance to another. So redox actually stands for reduction, oxidation. So oxidation is the substance that loses an electron. I've got the little positive sign there because if we're looking at its charge of the element, its charge becomes more positive when it loses an electron. Remember, electrons are negatively charged. So the thing that is undergoing oxidation or being oxidized, it is also called the reducing agent. That's an important vocab term to remember because it gets thrown out a lot. Just making sure you know that reducing agent is the thing being oxidized. So reduction is the element or substance that gains an electron. Since electrons are negative, when it gains an electron, its charge becomes more negative. As a little negative sign is showing us there. And the thing that's being reduced or undergoing reduction is called the oxidizing agent. When we're looking at oxidation and reduction, even though I have the little plus and little minus charges, that doesn't mean that the thing that's got a positive charge is being oxidized and the thing that has a negative charge is being reduction. That just means the thing that's being oxidized has a positive change in its charge. So something going from a -3 to a -2 is a positive change in its charge. Its charge is becoming more positive. And then reduction, becoming more negative, something +2 to 0 is being reduced, even though neither of those charges are negative. So we can't have two oxidations happening or two reductions happening. We have to have an oxidation and a reduction happening, which is why we can call them redox reactions, because reduction and oxidation always go together. So this is just a reminder of identifying this. When you're trying to determine if something is oxidized or reduced, you want to look at the charges of the elements involved. When we're looking at electrochemistry, electrochemists call charges oxidation numbers, but that's the same thing. So it's usually easy to look at reactions in their net ionic form when we're looking for their charge/oxidation number. Most of those charges are already visible. So in this reaction, the charges/oxidation numbers are in the little circles. So we can see that zinc starts out with a 0 charge and ends with a +2 charge. So zinc lost 2 electrons, meaning its charge became more positive, so it underwent oxidation. Hydrogen starts as a +1 charge and ends as a 0 charge, so its charge is becoming more negative, so it is undergoing reduction. So again, just a reminder, the thing that is reduced, so in this case is hydrogen, is the oxidizing agent. So the oxidizing agent would actually be H+. It's going to be the reactant of the element that is undergoing that change. So the thing that is oxidized, which is the zinc solid, is also called the reducing agent. So this is kind of the physics background stuff. When we're looking at charge, usually up until this point, charge, we've just said like electrons have a -1 charge, protons have a +1 charge, neutrons are neutral. Well, charge is actually something that can be measured, and -1 and +1 are just oversimplifications of that. So the electric charge is represented by the lowercase letter q, and the unit that it is measured in is coulombs, which is capital C. So there are only so many letters in the alphabet. So Q also stands for heat. We're not talking about heat in this chapter, so charge Q. So we could solve for the actual charge on anything with this equation. The lowercase n is how many of those charges there are in the molecule. The capital letter N is the number of moles, and F is the Faraday constant, the 96,490 coulombs per mole. So just for reference, I have down there that one electron actually has a charge of 1.602 times 10 to the -19th coulombs. Again, typically we think of electrons as having a -1 charge. Well, -1 is a lot easier to say than 1.602 times 10 to the -19th. So if you are following this equation for 1 mole of calcium ions, the lowercase n, which is the number of charges, there are two, because calcium has a +2 charge, so there are two charges in there. The capital N would be 1, because in this example there's 1 mole. So if there were 0.05 moles, then capital N would be 0.05. Faraday constant is always present. So I didn't actually do the math to work this out, but the lowercase n and the capital N are the two that you've got to that vary from question to question with this. So current, which is represented by a capital letter I, is the quantity of charge flowing each second through a circuit. So it's the charges per second. So the unit, which is amps, capital A, it's actually coulombs per second, kind of like joules is actually kilogram meter squared per second squared. It's kind of a shortened version of it. So amperes, amps is coulomb per second. It's charge per time. So when we're looking at the current in this chapter, we're looking at the electrons moving from the thing being oxidized to the thing being reduced. We're going to need an electrode, which is something that conducts those electrons either into the reaction if we're adding electrons to the reaction, or out of the reaction if the electrons are leaving. So in this case, platinum metal is our electrode. And potential, which is just the difference in potential between two substances. The unit for that is volts, capital V, which is an abbreviation of joules energy per coulomb. Okay. So there's just calculating work. Electrolysis is if we're doing a chemical reaction. So it's a redox reaction, but we have to apply volts because the reaction itself is non-spontaneous. So the electrons have to be pumped in from the outside, pretty much. We're forcing that reaction to happen by running electricity through the reaction. So electrolysis is forcing a non-spontaneous reaction to happen with electrons. So galvanic cells are mostly what we're going to be looking at. Galvanic cells are spontaneous redox reactions. So we don't have to add the electrons. The electrons will flow through the electrodes on their own. So it's a spontaneous redox reaction. All you have to do is introduce the species and the reaction happens. You don't have to force it. So in a galvanic cell, we actually separate the thing being reduced from the thing being oxidized. So in this picture, we see two beakers. One of them, it's the thing being reduced, and one of them, it's the thing being oxidized. We've got the metal like bars sticking out. Those are our electrodes. And then we have the wire attaching them, and then a voltmeter in the middle. So the wire is how the electrons flow from one beaker to the other. The salt bridge is what we use to keep electron neutrality. So the potentiometer is the voltmeter, the thing with the little meter with the capital V over it and the plus and the minus. So that's how we measured the voltage, so the difference in potential between the two beakers. So that salt bridge, it's a glass kind of U-shaped tube with sort of, I think like jello sort of stuff in there of some ionic salt that is not reactive, so it's inert. So in this example, you can see the potassium and the chloride in there. So they just made like potassium chloride jello. So it's thick, it doesn't just plop into the container. But electron neutrality, if you remember from our equilibrium chapter, all the plus charges have to equal all the minus charges in a container. So the reason why we have this issue, when an electron leaves the beaker being oxidized, lots of negative charges leaving the beaker, so the overall beaker would become positively charged. Well, that's not maintaining electron neutrality. So what the salt bridge does is in the beaker, which in this case it's the zinc beaker on there, when an electron leaves the beaker to travel through from the electrode into the wire, heading towards the other beaker, to balance out the negative charge that is lost, a chloride ion from the salt bridge just plops in there. So we lose a negatively 1 charged electron, we gain a negatively 1 charged chloride, so electron neutrality is maintained. That chloride is not reactive, so all it's contributing to that is it's now another anion negative charge floating around. When that electron that left the zinc makes its way over to the other beaker with the copper, once it goes from the wire into the electrode into the solution, that beaker is now negatively charged. Not okay. Again, that's not maintaining electron neutrality. So to cancel that out, a positively charged potassium ion flows into the beaker as the electron does, so we add a negative charge and add a positive charge so they cancel each other out. So the terminology for those two beakers, the cathode is the beaker for the thing that's being reduced, and the anode is the beaker with the thing that's being oxidized. Honestly, the way I remember this, anode starts with an A, oxidation starts with an O, they're both vowels. So anode and oxidation go together because they're vowels, cathode and reduction are consonants. Whatever, just know these terms. They're going to be used a lot in this chapter. So when we're looking at galvanic cells, which has to be a spontaneous redox reaction, the electrons are always going to move towards the most positive potential. Kind of like waterfalls, the water always goes from the top of the waterfall to the bottom. It doesn't ever go up spontaneously. So even though we talked about the reaction, it has to have a reduction and an oxidation in it, a lot of times they're written as half reactions, so just showing what's happening in one beaker. But even though one beaker, the cathode is reduced, and the other beaker, the anode, is being oxidized, typically they write both half reactions as if they're being reduced. Because there's tables and numbers, and they just chose reduction as the standard way to write them. So just don't be surprised when you see a whole bunch of reduction equations. So electrochemists have this line notation, a shortcut, to take a balanced redox reaction and write it in this line notation. It kind of shows the cathode and the anode. So we see these vertical lines. So one vertical line, it says represents a phase boundary. I think that's like reactants to products. It's the before and the after. The double line is the salt bridge. So in this reaction, so here's the same reaction, the last picture, but I just wrote it out. It's not in net ionic form here, but we can see it. So the two, well, the zinc is going from a 0 to a +2 charge, so it's being oxidized, so it's in the anode. The copper is going from a +2 to a 0 charge, it's being reduced, it's in the cathode. So the way they wrote it in the shorthand line notation is to take the two things for the anode, the reactant and the product, and separate them by one vertical line. Put the salt bridge in the middle, the two vertical lines, and then put the cathode on the right-hand side, so the reactant and then the product. So it just kind of breaks it into anode, salt bridge, cathode. So when we're looking at this voltage that we would get off that potentiometer, the voltmeter that's in the middle, that's the difference in potential between the two electrodes. On that last picture you saw there was a plus sign and a minus side. So you're going to see in this chapter, so again, the E stands for the voltage, the potential. If you've got a degree sign floating around in there, that just means that these are standard potentials. So in standard potential, they were compared to something that a half reaction that has a 0, which is the standard hydrogen electrode, the SHE, the She. So that was like the one beaker had the hydrogen electrode and it had hydrogen in it. And in order for it to be standard reduction potentials, we've got to be at 25 degrees Celsius, and everything is either one activity, which if you remember how activity works, it's basically one molarity times the activity coefficient, which still gives us 1, or if it's a gas, the pressure is 1 bar. So that's just the half reaction of the standard hydrogen electrode. So we would have H+, we'd have acid at 1 molarity, and hydrogen gas at 1 bar. So they had to assign something as 0. So this SHE, the She, the standard hydrogen electrode, was the one that was determined to be the 0. Kind of like when you tear the balance or blank a spectrophotometer, something had to be the 0. So this is hydrogen. So in this case, on the left, the anode in this reaction is the standard hydrogen electrode, and the cathode is the silver plus and the silver. So since the hydrogen electrode's potential is 0, the voltmeter, which measures the difference between the two, whatever the voltmeter reads, it'll be the silver potential minus the hydrogen potential. Well, if the hydrogen potential is 0, then what the voltmeter reads is just the potential of the silver only. So that's how they can figure out the potential of just one half reaction, is by comparing it to hydrogen, putting hydrogen in the anode, and whatever half reaction you're looking at in the cathode. So then the voltmeter, which does cathode minus anode, if the anode is 0, the voltmeter is giving us what the cathode always is. So this is just a very small table showing some of these half reactions. They're written as being reduced, so they're called the standard reduction potentials. So sometimes you see a subscript of RED in there. And if you look at the last column that's got the potential degree sign in volts, they are ordered from the most positive potential value to the most negative potential value. The most positive potential means it's got the most positive reducing potential. So it most wants to be reduced. It's the strongest oxidizing agent. Okay. The most negative potential value is the most negative reduction potential. So it has the least potential of being reduced, which means it's got the most potential of being oxidized. So as you go to the bottom of the list, like lithium down there, very challenging to reduce, but it is easier to oxidize. So it has more potential to be oxidized. So they wrote these tables in terms of reduction, because if they wrote it for oxidation, all we would do was flip the reactants and the products and change the sign on the number. So it was really not necessary. So you just need to remember that the more positive the value in reduction potential, the stronger the oxidizing agent, the more it wants to be reduced. The more negative the value, the stronger the reducing agent, which means the more it wants to be oxidized. Okay. So if we're looking at a galvanic cell, which again, spontaneous, the more positive reduction potential value is the strongest oxidizing agent, will go in the cathode. The more negative reduction potential value will be oxidized and will go in the anode. And so by looking at that table, if you're deciding which two elements you're comparing, you can figure out which one is going to be the anode, which one is going to be the cathode, just by looking at one of those tables.